lot of terminology, new types of geometries. When we think about strike-slip fault systems, we have an entirely different geometry that we want to think about, an entirely different development and sequence of development of features that have geometric elements, that have descriptive elements, and we want to think about how these different systems develop. And so when we're thinking about strike-slip systems, we really want to try to put them into context of where do we see them developing. And perfect timing. And when we think about the development of strike-slip fault systems, we really see three different settings for them. We see strike-slip fault systems that develop inside of a plate. And as an example, we have a fault system in southern Oklahoma called the Ouachita Valley Fault System that appears to be an intraplate strike-slip fault system. We have fault systems in India that appear to be intraplate strike-slip fault systems. We also have large-scale strike-slip fault systems that we sometimes refer to as wrench systems that are active tectonic boundaries. They're transform boundaries. And those would include faults like the San Andreas. San Andreas is a classical type of a transform boundary that we need to try to understand. How did that develop? What's going to happen in that system as we move forward? The Alpine fault system in New Zealand is again a classical transform type of a boundary where we're offsetting active tectonic elements. In the case of the San Andreas, we're actively offsetting mid-ocean ridges, spreading centers that we drew on the board. In the case of the Alpine system in New Zealand, we're offsetting subduction zones. So we have to have, in order to be considered a transform, or what your text tends to refer to as transcurrent, you have to have active tectonic elements like a subduction zone or a mid-ocean ridge that you are seeing offset on. And the strike-slip system in that is helping accumulate that offset. Then we have some rather intriguing escape features, and these are relatively younger ideas, new ideas to us regarding how we might see large-scale strike-slip fault systems develop in response to plate interaction during tectonics. So really, three different classes kind of fit under the general geometry of that system. We talked about the Riedel geometries, the shear sense of a system, and we used sort of interchange RR prime. This goes back to a classic paper that was published in 1929 in a German Geologische Rundschau about shear fractures, shear systems. Unfortunately, that paper has never been translated into English, and so you have to read it in the original German. This is quite a wonderful concept of what we're terming antithetic and synthetic faults. A synthetic fault, remember, as we talked about our geometry, if this was our through-going fault at depth, so this was our x prime, and I can't remember which one I called prime yesterday or Monday. This would then have a low angle set of faults that would develop at surface. These would be the R shears. They would develop early. This would be the synthetic. So if this is a right lateral system, the way I've drawn it, these would be right lateral in their behavior. Yeah?
So you'd call it right lateral synthetic?
If this is a right lateral fault at depth, the synthetic faults will show right lateral displacement. If the fault at depth were a left lateral, the synthetic faults would show left lateral displacement. They are simply occurring at a low angle, usually starting around 10 degrees to the 10.
Sorry, I didn't mean to interrupt you. With the term synthetic, the book uses it to refer to, I believe, faults that are pointing away from a major fault. Here, what does synthetic?
Synthetic means that they have a similar orientation and similar offset.
Or just to each other. Okay.
Well, if we have a right lateral fault system at depth, then the first faults that will come to surface are these synthetic faults, and they occur at a low angle relative to the through-going fault plane and will show the same sense of offset. Okay? So if this is overall right lateral, the synthetic faults will be right lateral. Then we have antithetic faults, and if you'll allow me to break this apart, we will have antithetic faults that come in later than the synthetic faults. They can connect up the synthetic faults. Now I've stripped out the folds, I've stripped out the synthetic faults here. This is our antithetic fault system. The antithetic fault system has the opposite sense of displacement. An antithetic fault system that comes in later, this would be our R prime, these are our R systems here. These would have, in the case of a right lateral system, these would locally have left lateral offset. So antithetic means opposite sense of offset relative to the through-going fault system. Synthetic means it has the similar sense of offset relative to the through-going fault system at depth. Now keep in mind, these patterns tend to be en echelon in character, piecewise offset. We take a geometric element, so imagine if we can pick up this particular fault, maintain its angular orientation, and simply repeat it at some spacing. That generates an en echelon pattern. Same thing here. If we were to pick this fault up, maintain its orientation, and then simply bring it in at some spacing, we repeat that same pattern again and again and again and again. So that is an en echelon geometry. Now I haven't added the folds to this. The folds will develop first in that particular system, then the synthetic faults, then the antithetic faults, and so we can end up with this beautiful array of faults and folds where the folds are being sliced up, offset in a wide variety of geometries in that particular system. And that led to the statement that a strike slip fault system could be considered to be what? A system that gives us lateral juxtaposition of dissimilar lithologies along an anastomosing bifurcating fault system. That is a beautiful definition. That is an example of, I guess, scientific obfuscation that makes it difficult to understand. The only one that I know of that's worse is the definition of a cactolith, and that is a thing of beauty. You should look it up sometime in the Geologic Dictionary. So we have these geometries that develop in cross-section. These have a tendency to take on the appearance of a flower structure. And what we mean by a flower structure here is, again, in cross-section. The flower structure will start off as a singular fault zone at depth. This would be a fault zone. You are not necessarily looking at one singular fault plane. It might be several faults very, very close to each other. As we move towards surface, what will happen is it will tend to flower out, get branches associated with it, and we can develop a rather interesting and narrow fault zone here at the surface where we might see multiple faults with different geometries as it progresses upward toward the surface. If we have localized a little bit of compression where we're seeing some uplift associated with it, we're going to call it a positive flower. If we have a little bit of extension associated with it, and we tend to be forming a down warp, we're going to call it a negative flower structure. So these can be both positive and negative in nature. Steve?
Could you draw the difference?
Okay, if we have a positive flower structure, what would happen in this case, let's make one that's relatively simple. Here, what we would see is we would see folding associated with this overall system. And so we would have a positive mound. This might be highly deformed, like so. So it's up in relief. If it is a negative flower structure, what we would look at is we would have what might appear to be a normal fault system that we're infilling locally, but it connects up to a strike slip. That would be a negative flower structure. So this is a negative, this would be a positive flower structure. We can see these in part when we have releasing and restraining bends. And we got some questions about releasing and restraining bends. The basic geometry of a releasing and a restraining bend is if we have a fault that is curved. Doesn't matter which way it's curved. We can have a right or a left curve on this. In this particular case, if we move this way, what's going to happen here? Extension. So that this would be a releasing bend in this case. So in this area, right in here, we would see releasing, we would see normal faults in the system. We might see a negative type of a flower feature in that area, and we could form what is called a pull apart. We could open up a local basin in that system and get conglomerates feeding into that particular basin. If that continues, it can become a much larger feature. Some releasing bends can have features that are tens to even hundreds of kilometers in size. In that case, we tend to call it, to give it a terrible word, a rhombochasm, if it extends greatly in that system. If we take the same curve, if we generate the same basic type of curve here, but now this is going to move that way, this is going to move this way. Let me exaggerate that curve a little bit more. So what's going to happen right here? Compression. This is going to be an area where we're seeing quite a bit of compression across this particular system. So in here, in this zone, we're going to see compression. So this is called a restraining bend, where we can see probably a positive flower. We might even see thrust faults, local, in that system. Some of those thrust faults may or may not actually cut all the way to the surface. And there are some cases, if we look at the San Andreas system, north of Los Angeles, as you move northward out of Los Angeles, in Los Angeles you're down on a flat. You look to the north, you see mountains. That is a restraining bend. That's where there was a fairly significant earthquake that occurred quite a while ago now that caused billions of dollars of damage. Luckily did not have significant loss of life, on thrust faults that had not been previously described, because it wasn't fully understood that you were dealing with a restraining bend there and what those implications were. Since that Northridge earthquake occurred, all of the emergency services and emergency planning had to go back and rethink what the ultimate possibility is for damage, for loss of life, and for distributing their assets for response. Now we understand that there are actually thrust faults coming out of the Northridge Bend underneath Los Angeles. One of them comes up right underneath the RCA building, and that is termed a blind thrust, a thrust that does not show up at the surface. And so if we looked at a cross section, what we would see are thrust faults coming out of this, some of which cut to surface, some of which do not. So this would be a strike-slip system with thrust faults. The blind thrusts may not make it all the way to the surface. They could contain significant amounts of strain energy that could result in an earthquake up to, the estimate is about 7.5 magnitude. The estimates right now in the emergency planning is if we had a 7.5 magnitude on one of these blind thrusts, either the Elysian Springs or the RCA, the potential loss of life could be, if it were during business hours, as many as 50,000 could perish in the initial earthquake because of the potential damage to buildings in that area. And so that's the planning right now for that particular area. Strike-slip faults can be devastating. If you recall, a few years ago, we had a magnitude 7.5, not a large by most measures. It's a large quake, but not a great quake. That occurred in Port-au-Prince, just outside of Port-au-Prince to the south. The total loss of life estimate is 230,000 perished in that one earthquake. Now, several reasons for the damage and for the loss of life in that particular earthquake. You were dealing with one of the poorest countries in the world. It was under UN control. The government was effectively functionless at the time. You did not have any building codes, so buildings did not conform at all to being able to handle any type of lateral energy. So much of the infrastructure, most of the buildings simply collapsed. The vast majority of injuries and fatalities were related to crush when a building collapsed in that particular system. There was no response. The government was unable to respond to the tragedy, to start search and rescue in that particular system. The UN mission there was lost because the building that all of the UN managers were in for a meeting collapsed, killed them all. So there was no high-level response. The first response for that particular earthquake actually came from Iceland, not the US. Iceland was the first emergency response team there. The first hospital team there was from Israel. Again, not the US, not Europe, not the larger countries in the vicinity. So there was a very odd response. And all of this piled up and led to that great loss of life in that particular system. That particular system was slightly compressional and strike-slip in that area. Yeah.
Kind of like the odd response For Katrina, Venezuela actually lowered the prices and gave some oil to the U.S.
Right. We had a terrible response to that emergency as well. So these systems, these strike-slip systems can be dangerous. When you look around at the greatest earthquakes that have occurred, the greatest loss of life, most of them are either a strike-slip or they are what we termed a megathrust type of earthquake, the Indonesian quake that occurred on Boxing Day. That was a megathrust quake. The recent quake that we had in South America was a megathrust type of quake where you have a subduction zone that gets locked and forms a plate and then it rebounds very, very quickly. That would be a megathrust. So these are all the geometries that we can have within a strike-slip fault system. As the fault system develops from basement towards surface, you can see all of these geometries develop into what we consider to be a classical strike-slip fault. So the geology can be kind of complex. It can be beautifully complex, particularly if you throw in that we can have strike-slip fault systems that are extensional. So rather than having a strike-slip that is purely strike-slip, we can have one plate move away. So we end up with normal faults, with listric geometry, and all of these structures. Or you can have a strike-slip fault system that is convergent, transpressional. So you have thrust faults and all of these structures. So strike-slip can give you, in some cases, if you think about all the terms and all the geometries that we've seen, it can give you an all of the above kind of an answer, which can be maddening. It can be sometimes difficult to work these systems out. So let's look at a few of these, see if we can analyze. Then we have a group challenge. And we can start the group challenge. We should be able to start it in class, but it might be something you want to finish out. Yeah.
Quickly, with transpression and transtension, I'm sorry, what do those refer to?
Those are if we have, imagine if you will, Tim, if you will allow, I will put our XX prime up here, okay? What we were talking about before was an XX prime that was this type of a geometry. This plate is trying to move laterally relative to this plate. Simple strike-slip. If we have transpression, what is happening instead, and let me use a different color, is we have this type of displacement. That would be transpression. So we would see strike-slip and all the characteristics of a strike-slip, but we would also see thrusting, compression associated with that system. Or if we had a system that was moving away. So what if we have this? It would be opening up. So we would find normal faults, listric geometries, plus these. So we can end up with some intriguing geometries and some intriguing complexities in that particular system. Does that make sense? Now, let's look at a few features around the world, and then we can dive into our challenge. Now, first off, let's take a look at Asia. The other day I described this as potentially being an escape complex. If we just start doing an analysis of what appears to have happened, if we look at the system, this is Afghanistan here. Pakistan is over in here. This would be the Kashmir region. This would be the high Himalaya, Nepal into Tibet. As we get over in here, we would get into the Indian state of Arunachal Pradesh, which is basically eastern sun to India. This gets into Myanmar in here, Burma, down into Malaysia. This would be the Andaman Islands, Southeast Asia, so Vietnam would be in here. This is in China, and then we're moving northward as we get into Mongolia. This would be the Koreas, Japan's over here. What do we see? Well, if we start piecing this together, look at how this thrust belt curves dramatically here. It curves dramatically over here as well. If we were to pull India back, we can measure how far India has pushed into China, into Asia. I guess geologically we don't have any borders on here. So into Eastern Asia. India collides and continues to move northward. And so here we have this system continuing to move northward. What has to happen? Well, something has to give. And so what happens is that we see initially Southeast Asia transform and move out along this boundary right here. This is the Red River Fault Zone. Cuts through Southeast Asia into Vietnam. Yeah.
Did you say river?
Red River.
Red River.
Red River Fault Zone. That's the Red River Fault Zone. And you have an interesting demarcation in petroleum systems in Vietnam based on the Red River system. Then we come up and we see here a large block that is apparently rotated, another large block here. We see a zone in there, that may be shears in this system. This is the Tanshan system in here. As we move further north, this all looks like it's being squeezed up this direction. This curvature right there, that curvature right there, this curvature right there are highly diagnostic of escape features. So as India has pushed into Asia, and it's still moving northward, we're still seeing uplift in here. The recent earthquake in Nepal is evidence of that continued displacement in that system. First, Southeast Asia was squeezed out and down. China has been squeezed outward. So it's moving this way. This system is being squeezed. If you look at the drainages, we see another system up here. This has been squeezed outward based on the collision with India. That outward displacement has caused the opening of the Baikal system. Lake Baikal is what has been termed an impactogen by John Dewey in a now famous talk that he gave at a scientific conference, where he said he didn't want to introduce any new terminology into the literature. He hated the term impactogen. He never wanted to introduce the word impactogen, and then he proceeded to say the word impactogen about 50 times during his talk. And so by the end of the talk, that was part of our nomenclature now. Yeah.
How do you spell that?
Impact, O-G-N. So this is, if you imagine, this has been squeezed out and down. This is being squeezed outward. That's being squeezed outward this way, so it separates right here. This is a normal fault-bounded lake that is roughly 1 mile deep, fresh water. This is the largest freshwater lake on the planet. It holds just at 20% of the fresh water in the world. Is all located right there in Baikal. And so if we look at this instead of from our shuttle radar, if we look at it as a geologic map, this is what we interpret. This is from a classic paper that started these concepts. This was by Tapanier in 1982. Here's India. You can see the interesting bend and some of the complexity. Here is a strike slope system. So all along Pakistan-Afghanistan boundary, in what we would call the Hindu Kush, that is a large-scale strike slope system. We have the oroclinal bend here. This would be the high Himalaya. Look how that thrust system bends around. Comes on out. This is Southeast Asia being pushed outward and downward. Red River boundary here. Red River is still active. That's the Red River shear zone. Is still active. We have another shear zone down here in Indonesia. We have this being squeezed outward here. Along the Tian Shan, Mongolia, Siberia are being squeezed outward, forming Baikal. Yeah.
Does this squeezing have any impact on how a lot of that Mongolia area is like all deserty?
No.
No.
But it significantly impacts the behavior structurally. So this is the tectonic interpretation of this particular system. That helps us understand the assembly. That is escape in that system. And the basic idea is this. If you take a plate and you squeeze it, so I'm going to take, this is going to be a plate here, and I'm going to have a collision here and here, what's going to happen?
It goes flying.
So China, Southeast Asia have gone flying. As the result, now where did it go? As the result of the impact of India. The requisites are that the Indian plate is relatively old, thick, and strong. So it's not crushing. We have a free edge over here. So things can displace. We can move things because the only constraint is subduction zone, subduction geometries. So Japan, that curvature of Japan.
Okay, how fast are they being squeezed out?
Today, this is moving just a few centimeters a year. In past, it was moving up to 50 centimeters per year. Pretty quick before the collision. So this is our escape type of geometry. We see this in other places as well. We see this in Mediterranean. Here's a shuttle radar of the Mediterranean. This would be the Atlas Mountains in here. These correspond in part to the Appalachian Taconic Acadian system. We have Red Sea. This would be the Persian Gulf. This is the Zagros in here. You can see this rather interesting oroclinal bend. We come across into the Alpine system over here. As we go further, just to connect up, this would be Afghanistan in here. Afghanistan towards Pakistan. So this would be the Hindu Kush in this particular area. What we see is this zone. Do you see this fault zone right there? In northern Turkey, that's the Anatolian Fault. Northern and southern Anatolian Fault. This was a collision. And what, can you tell me what happened to Turkey? It got squished and extruded. It's an escape feature.
Which
And
way
so
did it squish out?
the geometry is such that this is now Turkey. We're going to put Turkey in the vise here, and it gets extruded out this way, bounded by the northern Anatolian and southern Anatolian fault. Very, very active fault system. The last earthquake, now I've lost the cap. The last earthquake that occurred along that complex was in 1999 in Izmit. Roughly 30,000 people perished there. The next probable quake would be in Istanbul of similar magnitude. There's a lot of discussion and debate about whether it steps across the Bosphorus, whether it will actually move into Istanbul, or if it moves back to the border area here. There's now some suggestion that it may step back. But what happens with the earthquakes is they propagate across. Yeah.
So there's a north and a south.
Mm-hmm.
Do they act at the same time, or is it one at a time, or I mean, how do
They behave very differently.
Very differently. Okay.
Very, very differently. This one is really much more extensional, does not have the severity of earthquakes at all in that system. So this is the escape type of feature. And just, you know, get the visual of taking something like this, squeezing it, what happens? It extrudes. So Turkey has been extruded into the Mediterranean system due to this collision that formed the Zagros system here. So this is a convergent boundary all along here. If you recall, when we were talking about thrust-related petroleum systems, this is our thrust-related petroleum system here. We're in the Foreland Basin, here's our thrust system. Same types of principles are involved in analyzing that particular petroleum system. So this is an escape type system. The last thing I want to look at is a rather intriguing treatment of how the San Andreas Fault developed. If we go back about 40 million years ago, North America is moving towards the southwest at a rate of over 50 centimeters per year. So it is screaming towards the southwest. It accidentally runs over the East Pacific Mid-Ocean Ridge system. Let's see if it'll play again. So it collides with the East Pacific. We completely swallow up portions of the Juan de Fuca Plate, and we then have to form a transform. This is the transverse ranges here. The transform develops, the San Andreas system then becomes that transform from Mid-Ocean Ridge in the Gulf of California to Mid-Ocean Ridge off of Cape Mendocino in that system. Because the North American Plate ran over the Mid-Ocean Ridge. The best analogy I can think of, and you know, my daughter will eventually forgive me, when I was teaching my daughter how to drive, we would cruise around in parking lots, you know, practicing how to shift. She learned on a standard. We don't know how to drive an automatic in our family. So we were cruising around a parking lot, and we accidentally ran over one of those parking bumpers. So we were cruising around, that's what happened to North America. It was just learning how to drive, having a great time, ran over the East Pacific lines. And so we had to transform across. So that is what happens in this system. That's why the San Andreas is a transform fault. This starts at about 38 million years ago, 40 million years ago, and you can see the progression of time over here. I will load this movie onto Harvey. This is part of Tanya Atwater's collection of animations. Tanya is, she's retired now, but she's probably one of the most famous structural geologists in the world, tectonicist, unbelievable. And she's done a lot of work on these types of animations, on evaluating the tectonics of this system. And so I will put this up on the Harvey website. Yeah.
You mentioned something about a mid-ocean ridge.
Huh?
What was it?
The East Pacific Rise, the East Pacific Spreading Center in the Pacific Ocean,
Where in the Pacific is it located?
in the East Pacific.
Right. So I mean, relative to California, how close?
It's right, it comes, since we subducted it,
Mm-hmm.
it is right along the boundary. The Pacific Rise is right there.
The red part?
Huh? This right here, this is the Pacific Rise. So here's the collision. Now we start forming Gulf of California, transverse range, and we're going to move northward.
And this one is also the escape, or no?
No,
No,
no.
it's not. Okay.
This is the transfer system. Now, each of you has a card that has a number, 1 through 7. Your task is to grab one of these and the geologic map in this, and to do an analysis, determine what type of structural system you're looking at and document it. So find your corresponding partners